You have seen how to find the area between two curves by integration. Next, we're going to take a look at how to find the volumes by integration as well. So first, we're going to take a look at volumes by slicing. The volume of a solid bounded by two parallel planes, for example, these circles on the ends, they are perpendicular to the x-axis, and it can be found by slicing. So we'll assume then that the x-axis is here, and these circles are perpendicular to the x-axis. So the volume of this shape, let's take an arbitrary cross-section. So if I cut this shape right here, I'm going to have the area of one cross-section but then I need to times that by my height, or I guess in this case it's my length since the cylinder is lying down. But I'm still going to just call it height to make it easy. So the volume is equal to the area times the height. So this is quite straightforward because the circle is the same size whether it's from the left end to the right end. But what happens when the cross sections are not the same size? So for example, you can see this shape here on the side, it's a trapezoid, but on the ends, it's a rectangle. Now, if we start on the end here, we have a small little rectangle, and then as we move to the right, we're going to get a bigger and bigger rectangle. So let's choose a rectangle that's inside here. Okay, so you have to imagine, it's hard to draw this in 3D, but imagine this is a 3D object here. So we're going to take one rectangle, the area of one rectangle, and then as it's growing, we need to take that into account. So this is where the integral comes in. So we'll say that this is A and this is B. So we're going to take the area of each of these rectangles, and then we're going to times by dx. So we're going to say that A of x is a cross-sectional area perpendicular to the x-axis, and then we're going to say that dx is the width of this one slab. Now, when I integrate from A to B, that is saying that I'm going to add up all of these rectangles from A all the way to B. So it's going to be an infinite number of rectangles. And we're thinking that each slab will get closer and closer to a width of 0. So this brings us to an example here. So to find the volume of a solid with a base, we're going to start by finding the area of one slice. And remember that the base of this slice will be plotted on the coordinate system. So you're going to use that as your function. Each slice will have a width of delta x, and then you're going to integrate from A to B. All right, so let's take a look at this example here. So we have a solid. It has a circular base of radius 1. And then we have parallel cross sections that are perpendicular to the base that are squares. So we want to find the volume of the solid. So we're going to imagine that we have a circle, and I'm going to draw the base on here. So the base is a circle of radius 1, and then we're going to draw parallel cross sections that are perpendicular to the base. So now it's very hard to draw, but let's say that we're going to draw a square. Oops, let me try this again. So we're going to imagine that there are squares and an infinite number of them going like this. Now, as we get closer and closer to the end of the circle, the squares become smaller and smaller. So let's take a look at this image here that I found in Google. So here are some square cross sections. And this one's very nice and smooth, and it should be nice and smooth if it were perfect. So we have square cross sections, and then the base here is circular. So what we're going to do is we're going to start off with the equation of the circle. So it's going to be x minus h all squared plus y minus k all squared equals to r squared. Now in this case, our circle is centered at 0, 0, so our h and k is 0. Therefore, we have x squared plus y squared, and our radius of the circle is 1, so it's going to be 1 squared. So we're going to isolate our y, and the reason that we're doing this is, even though I didn't state actually in my problem, we're going to assume that the cross sections are parallel. The parallel cross sections are perpendicular to the x-axis. So because it's perpendicular to the x-axis, we want to write our equation with y isolated and then in terms of x. So this length here, y equals to the root 1 minus x squared, is the distance from the x-axis to the top of the circle here. So that's root 1 minus x squared. So if I want to find the base of this square, I need to take this length and then double it to then give me the entire length from the bottom of the circle to the top. And this will be the same for all points on this x-axis. So therefore, the base length is going to equal 2 times the square root of 1 minus x squared. So we're going to take the positive here because we're looking at volume and it's easier to work with the positive length. So if I now have the base length, I can now find the area of one cross section. Now, the shape of one cross section is a square, and since we have one length or one side of the square, we can find the entire area by squaring this length. So we have 2 times root 1 minus x squared, and then all squared. So now we can find the volume. So the area of one cross section is going to be 2 times root 1 minus x squared, all squared, times the width of that slab, which is dx. And then we're going to integrate this from -1 to 1 to get all the different sizes of squares that make up this volume. So we're going to put the integral from -1 to 1. Okay, simplifying, we get -1 to 1. So this will be 4 times 1 minus x squared dx. And this will give us the volume equal to, so we have 1, so that's going to be 4x. And this x squared is, when we integrate, is going to be x cubed over 3. So we have 4x cubed over 3. And this is from -1 to +1. So finding the volume by plugging in 1 first, we get 4 minus 4/3, and then minus, plugging in -1, we get -4. -1 here, we get plus 4/3. And then we get 4 plus 4, so it's going to be 8. -4/3 minus 4/3 is going to be -8/3. And then when we subtract, we're now going to get a volume. So 24/3 minus 8/3 is going to be 16/3 units and then cube. So what we've done is we found the volume of this shape, which has a circular base and square cross sections, which, like I showed you, looks something like this.